Anytime. Good afternoon, everyone, again. This is our lecture 41 in high-dimensional probability and applications in data science, and this is the last lecture of this course. The topic today is concentration of measure. Concentration of measure. All concentration inequalities, all tools that we have developed so far, and the tools that are available in classical probability theory, such as the law of large numbers, the central limit theorem, and the tools that we have studied here, Hoeffding's inequality, Chernoff, Bernstein, Matrix-Bernstein's inequality, they all apply for linear functions of independent random variables. Classical tools of probability theory. They usually are for linear statistics or linear functions of random variables. Sums, right? The sum of independent random variables, that's a classical object, and the sum is a linear function, obviously, of random variables. Today, we will talk about what we can do if you have a nonlinear function, and that is actually a very common situation. It's unrealistic to expect that in the nature all dependencies are linear. And what can we do if we have a nonlinear function of independent observations? How can we handle that? So today, nonlinear. It turned out first with observations of Poincaré, and then partly Einstein, and then through the classical work of probability theory through Lévy, and then in the 70s, it turned out that linearity per se is not needed so much. What is actually needed is that the function, or observable in physics, the function depends somehow smoothly on the observations, not too like it's not too wild, not wildly oscillating. For any function like that, for any function that's not too bad, we can develop a similar theory. This theory, the theory of concentration, has the same power as for linear observations. This is very, very surprising, actually, that we can prove something like this theorem in such generality. So watch and see. This is called Gaussian concentration. Concentration of measure. We look at any nonlinear function that is Lipschitz, an L Lipschitz function. That's what we mean by smooth, relatively smooth. L Lipschitz function simply means that f of x minus f of y, the increments, are sublinear. So it's less than L, some fixed constant, times x minus y in the Euclidean norm. If in this definition you divide by x minus y, then you have f of x minus f of y divided by x minus by the norm of x minus y. It looks like the derivative already, right? This looks like something that if you move x close to y, you will discover the derivative. So Lipschitz definition is something more relaxing than the differentiability. In particular, all differentiable functions are automatically Lipschitz, but not all Lipschitz are differentiable. I gave that definition. For example, a function like absolute value is a Lipschitz function, but it's not differentiable at one point. So suppose it is a Lipschitz function, and we look at a collection of normal random variables. So let's put them all together in one random Gaussian vector in dimension d. So that means that axis has d coordinates, x1, x2, x3, and so on, xd, each of which is independent and standard normal random variable. Perfect. Okay, so here is an amazing result about f of x, the nonlinear function of a random vector. F of x will concentrate near its expectation. And we are looking at the bad event. So what is the probability that f deviates farther from its expectation, farther than t from the expectation? It's very small. It's Gaussian. T to the minus t squared over 2l squared. That's it. That's the theorem. For example, if f is linear, if f is, for example, the sum of these xi's, then you will just recover the Gaussian tail. Because then f of x, the linear combination of independent normals, will be a normal random variable. So we'll have a normal random variable and you have a Gaussian tail. Just a classical thing for the normal random variables that we studied before. The point of this theorem that f does not have to be linear. It can be any very much nonlinear function, and we don't need to know it. We don't need to know much about it. Before we go into the method of the proof, which is beautiful by itself, let me ask if you have any questions about the statement of the theorem setting. Good. Questions? If you have anything, any observations, interrupt me. Cool. Okay. There are like dozens of proof of this now. It is so beautiful, so elegant, and so general that the natural temptation of every mathematician is try to prove it with their own tools. And so now we have a lot of approaches to this theorem. I don't even know who first proved it. The proof that I will give now is historically the first, and it is based on geometry. Almost purely a geometric proof of this. The proof will actually be based on the isoperimetric inequality. Isoperimetric inequality. All right, so what's isoperimetric inequality as we know it? It says that if you look at all subsets with given volume, then what subset will have the smallest area, smallest perimeter? What is it?
The sphere, probably.
The sphere, exactly. Yeah, that's why the droplets of water the droplets of water tend to be round, because nature tries to minimize the sphere given the volume. So yeah, so among all subsets of given volume, and in fact, this theorem is true in any dimension. Of a given volume, the sphere, the ball, the Euclidean balls, the round balls, have the minimal surface area. So if I draw any set like this, for example, and I have a set of the ball of the same volume, let's say this is A and this is B, this area is smaller. So larger, the ball, this area is smaller. this surface area. I'm looking at on the in 2 dimensions that I draw it, the volume corresponds to the area, and the area corresponds to the perimeter. But let's think that we're looking at the space. So this is volume inside and the area outside. Okay. So this is a theorem. It can be proved by purely geometric means, can be proved by Fourier analysis. What a few people know that there is a generalization, a little strengthening of isoperimetric inequality. And let me explain it to you. The strengthening does not use the concept of area at all. So here is a strengthening. Take the set A and consider its small neighborhood. Just include all the points here that are a distance epsilon from A. So look at A epsilon, all the points that have distance at most epsilon. So for which there exists X, this is Y, for which there exists Y in A that is within distance epsilon. Yeah, clear? It's just like an epsilon neighborhood of it. Okay, the surface area. The surface area of A can be reconstructed by just looking at this shell here. So the difference between the sets A epsilon and A, and then just let epsilon go to 0. That's how you get the area intuitively, right? So this is, you look at the volume of the neighborhood, you subtract the volume, the original set, you get this shell. Then you divide by epsilon to normalize, and you take epsilon down to 0. Then if the area exists, if it's really smooth and so on and so forth, then it can be proved that it is the same. But generally, it's useful to have that even if the area doesn't exist. So this is very fractal object or something like that. This is called Minkowski content. A generalization of isoperimetric inequality, a strengthening of isoperimetric inequality, says that not only the area, but for any epsilon, the volume of A epsilon is minimized by both. So for any fixed epsilon, among all subsets of fixed volume, of a given volume, the Euclidean balls, again, minimize, and here I don't write the area, I write the volume of the neighborhood. This version immediately implies the classical isoperimetric inequality if you let epsilon go to 0 and you use this limit. Yeah. So it's clear that it's a little strengthening, and you can prove it also by symmetrization, I think. Good. That's isoperimetric inequality in RD. Any questions before we try to build a bridge between this isoperimetric inequality to the Gaussian concentration? Good. Good. All right. So isoperimetric inequality applies to the concept of volume, or the Lebesgue measure, just a usual measure on RD, uniform measure on RD. But you can ask it for other measures. You can ask if the isoperimetric inequality holds for other classical measures. For example, for the Gaussian measure. right? The bell-shaped curve. The Gaussian measure concentrates more around zero than away from zero. What is isoperimetric inequality for it? Just replace the notion of volume by Gaussian measure. And that's it. So the question is now whether the same thing holds for the Gaussian measure. So Gaussian isoperimetric inequality, where we replace the volume by the Gaussian measure, which has this density, the density of the standard normal random variable. So gamma of any subset of Rn could be defined just as a probability that the standard normal random vector takes value in A. Or analytically, because we know the formula for the density, that probability is obtained by just integrating this density on A. The norm of X is Euclidean norm, of course, dx. So here in this example, the Gaussian measure of A is just this area under the curve. Okay, so we have Gaussian measure in RT. It's not a uniform measure, it's more concentrated near zero. And then we ask ourselves the same question again. Among all the sets with given Gaussian volume, Gaussian measure, what minimizes the Gaussian area or the Gaussian measure of the neighborhood? What is it round? Is it not round? Round ball. Is this the same solution as in the classical isoperimetric inequality? What do water droplets look in Gauss space, basically, right? You drop a particle of water, does it want to be round or not round, for example? What do you think? What could be reasonable? Okay, I'm going to tell you, it's not round. All right, so the round balls do not minimize. It's going to be a different solution. What could be the reasonable candidates? It's a difficult question, actually, right? The Gaussian measure is so uniform, it's so round, it's so symmetric, right? It's rotation invariant. If not round balls, then what else, right? The thing is completely rotation invariant. How do
some square? Some
square, you know, not the square. Okay, I don't know how to prove.
Maybe it depends on the location, depending from the center. Like it's like ellipse that points towards the center or something like that.
Yeah, even more radical to that. Yes, but the solution is even more radical than ellipse.
Может, це конус, я не знаю.
Може конус. Conus, yeah, it's even more radical than that, actually, than the cone. It's a half space. Oh, sorry, Katrina. Half space. That's it. So it's just, you take a hyperplane and all of the, like, to the right of that hyperplane. That's all. So it's very, very infinite. Like I said, it's radical because it's infinite in all directions except one. Even more radical than cone. Very strange, but yeah, this is a theorem. Gaussian isoperimetric inequality. And unfortunately will not prove it. Among all subsets of RD with a given Gaussian measure, the half spaces minimize the Gaussian measure of a neighborhood. Yeah. And by half space, we simply, by half space, I simply mean excuse me, so I simply mean something like this. So if you have a line in the space, sorry, not a line, if you have a hyperplane, and then you look at everything that's, let's say, below to on the one side of that hyperplane. So that's a half space. There are several proofs of that. One that I know of is uses it has to use symmetrization in somehow. So it's like you take the set that's not a half space and you try to kind of move it toward the half space. Well, you can either do it by using Brownian motion. There is Brownian motion proof of that, and there is also a simple proof by Bobkov that has a flavor of symmetrization, but not quite. So this is Gaussian isoperimetric inequality. Equivalently, you can state the Gaussian isoperimetric inequality in the following way. If the Gaussian measure of A is larger than the Gaussian, not equal to, but even larger than the Gaussian measure of some half space, then the Gaussian measure of the neighborhood is larger than the Gaussian measure of the neighborhood of that subspace. The isoperimetric inequality itself says if the Gaussian measure equals to that, then it's larger. But obviously the thing is monotone here, so that is also true. Okay, so this is Gaussian isoperimetric inequality. Any questions? Cool. Okay.
Sorry, so in general, the main difference is that in the first problem we have like infinite measure, and so probably for all finite measure it should be expected that those sets should be unbounded. Yeah.
Yeah, that's a good question. I don't know. It could be unbounded. Whether it should be unbounded, I don't know. Yeah, probably. Yeah, I don't see how it should be unbounded, but yeah.
Yeah, so that's the question. Is it only for Gaussian, or like any finite measure will like have this unbounded set?
Yeah,
which
that's what I'm thinking about now, and it looks like the examples that I know are like that. So yeah, I'll give some examples after the proof of the original theorem, and the examples that I know for finite measures, they are all kind of infinite sets. Yeah, you're right. It's probably Yeah, you can intuitively think of infinity as a point. It's like in a projective space in some sense, right? And since the measure decays so fast toward infinity, you can kind of think of infinity as one point. And so this half space, you can think of it as a neighborhood of infinity. It's like a round ball around infinity, if that makes any sense. So remove some point toward infinity, and then what you see as a half space is actually a round ball with very, very small curvature. Right? It's an extremely large Euclidean ball, but centered at infinity. And that's, of course, is possible because the measure is finite. So this ball doesn't have infinite measure. Yeah. And it's a good observation. Good. Any other questions or observations? Good. Gaussian isoperimetric inequality. We have that. And then let's establish this bridge between the Gaussian isoperimetric inequality, this theorem, and the theorem that we're going to prove now, Gaussian concentration. So let's look at it again. We have a Lipschitz function, and we would like to show that this Lipschitz function is almost a constant, essentially. So it doesn't deviate from its expectations too much. Not more than the Gaussian. So, good. Let's do it. Proof of Gaussian concentration theorem. We will first prove it. It turns out that it is easier to prove the theorem for the median than for the expectation. I'll explain why. So let M be the median of f of x. Then at the very last step, we'll move from median to expectation. But suppose we're doing for the median. The median is defined for any random variable as a number that breaks the probability space into two equal halves, right? Like 50% of houses are sold less than this, and 50% of houses are sold larger, for more expensive than this. This is a median. So probability that f of x is less than the median should be 1/2, and probability that f of x is larger than the median should be 1/2. And maybe there is an ambiguity around 1/2 for discrete random variables, for example. So if I define it like this, then the median exists. Okay, so it's any number that satisfies this. Good. Okay, so what we're interested in is to showing that f does not deviate too much from now its median. So let's look at the set, the level set, where f is less than the median, less than or equal to the median. And we will apply the isoperimetric inequality for that set, where f is less than the median. Well, gamma of a, the Gaussian measure, is greater than 1/2. Is this clear? Gaussian measure of a is the probability that the random variable, that f of x is less than the median, and this is greater than 1/2. I'm just interpreting this inequality here. The Gaussian measure is greater than 1/2. So it makes sense to compare the measure with the half space, with the corresponding measure. All right? The half space whose Gaussian measure is 1/2, what is it? Or a half space whose Gaussian measure is 1/2. It passes through the origin, right? Because things are symmetric. It would be 1/2 to the right, 1/2 to the left. So h is like this. H is h is this, for example. So h, let me move this around a little. H is all points in Rd that, for example, I can say the first coordinate is less than 0. It doesn't matter which half space I take. All of them have the same, that pass through the origin have the same measure. So we know that Gaussian measure is 1/2, and that's the Gaussian measure of H. Agreed? Okay. Therefore, here, therefore, the Gaussian measure of the neighborhood is greater than the Gaussian measure of the neighborhood by the isoperimetric inequality. H epsilon. H, let's do HT. HT. Good. Okay. Now this is H over here, H. Where's HT? If I make a neighborhood, if we make the neighborhood, we're enlarging H a little bit, specifically up to T. So this is HT. Sorry. This is HT. Agreed? Good. So HT analytically, it's this set of all x whose first coordinate is less than not 0 but t. Now just increase it. Okay, now we're moving back to probability. Gaussian measure is just a probability that the Gaussian random, the normal random vector takes values there. So it means that the first coordinate of the normal random vector is less than t. I'm just interpreting this probabilistically. Good, and that's very simple. That's computable. Right? We just have x1 is what? x1 is the first coordinate of the standard normal random vector. So it's just a standard normal random variable itself. I'm not saying it's computable, it's just a tail. Let's look at the complement. It's going to be the tail of x1, the tail of the standard normal random variable. Let me informally write it like this, greater than t. Good, and we know what it is. The Gaussian, it's a Gaussian tail. So it's like this. And this is t, and we're looking at this probability. And it's going to be very, very small. And we showed in one of the first lectures that the Gaussian tail is e to the minus t squared over 2. Good? So far, so good? Okay, so that was the first step in the proof. What have we achieved so far? We want to show that f does not deviate from its median too much. We looked at the halves, the sublevel set, this one, and we proved that its neighborhood is extremely large. We just increase it by t, and suddenly the probability is near 1. Okay, perfect. And now we claim that the set, that this neighborhood, is included in the points which we want. Included in the points for which f of x is less than m plus t. Remember, A is all points where f of x is less than m, and we're claiming that at, is included there. This is the only point in the proof where we'll use the Lipschitz assumption on the function. It's very simple. Let's check this. So suppose that x is here. X is in at. What does that mean? It means, well, what's the neighbor? Let's think about the neighborhood. The neighborhood means that there exists some point in A that is t close to x, right? That was literally the definition of the neighborhood, how we defined at. But f is Lipschitz. You know what? I hate to have L Lipschitz. f is 1 Lipschitz. Let's do without loss of generality. Or for simplicity, let's assume L is 1. So let's assume that f is 1 Lipschitz. And if it's 1 Lipschitz means that f of x minus f of y is less than t. Yeah. If x and y are close, therefore f of x and f of y are close. That's Lipschitz. Okay, so that means that f of x is f of x is less than, by triangle inequality, f of y plus t. And that's it. Y is an A, and in A, f of x is less than m. So this is f of y is less than m. So that means that this is less than m plus t. Yeah. Yeah, just forget this technicality. Just think. So if we have A, and on A, we'll know that the function is less than some value, and we increase A a little bit, just include the small neighborhood. F is Lipschitz. So what's going to be the cost of that? Very small cost, right? The neighborhood is just very close points, and so the Lipschitzness, well, we just pay t. So that's what we did. We paid t here. That's it. And then we're one line away from the proof. What have we achieved? We take the set that's at least one, we take the set like this. We increased its neighborhood. We proved that it is very large. And so the probability that f of x is less than m plus t, therefore, is greater than the probability that x is in AT. Here I'm just using this claim. This is the Gaussian measure of t. And the Gaussian measure of t, we proved that it is, we proved that it is large right here. X minus t squared over 2. Yay! I think we're done. Almost done. So this is, we proved that, in other words, f of x minus m greater than t is small. I passed to the complement here. There we go. And then we just repeat it for minus f instead of f, and we get the conclusion. The conclusion is with the absolute value here, and we pay factor 2, but I'll skip that. So we repeat it for minus f, and we get that probability that f of x minus m is greater than t. It's less than twice e squared over 2. Just add the two bad events together, union. Done. Oh yeah, I forgot. So we only proved for the mean. Let's skip the for the median, but we need it for the mean, for expectation. Let's leave it. Replace by the expected value of f of x. Replace the median by expectation. Do it yourself. It's a simple exercise. And it's in my book. If you ever get stuck in it, it's like 3-line exercise. Done. This is all the proof. Very geometric, right? Any questions about the proof? It's a very strong proof that it basically it says that the worst possible scenario here is when the function is actually linear. Why? Because for the linear function, the level sets will be half spaces. Right? And the proof went by the reduction to the half space. So basically we said, whatever our function is, let's reduce it to the half space, and even the half space is okay. So the logic of by the logic of the proof, the worst case scenario, the worst concentration is for linear functions. Any other nonlinear, it's crazy. Any nonlinear function is better than linear, actually, in this respect. Totally. How can this be true? But that's true. Good. Any questions?
I have one. So
yes, Denis.
Can we interpret that this theorem is that we can construct from normal distribution of Gaussian variables? Can we treat it like that? And is there?
I didn't catch that. Can we interpret it so that we construct what from what?
From normal distribution, make sub-Gaussian variables, random variables.
Sub-Gaussian because of f, like f of x will be sub-Gaussian. That's what you're saying?
Yes. If f is Lipschitz.
Yes.
And is there other way around? If we have sub-Gaussian, is there some Lipschitz function, or it is not possible?
Mm-hmm.
Is there
yeah,
connection?
Yeah. Thank you. Thanks, Denis, for asking. This is a very good question. Let me repeat what Denis says. If you look at this tail, it simply means you can interpret this as f of x minus its expected value. So f of x is sub-Gaussian. Right, that's all it says. And the sub-Gaussian norm, in fact, if you still remember, well, if not, that's fine. The sub-Gaussian norm is less than L. That's a conclusion of it. So from a normal random variable x, by applying some function, Lipschitz function, we get a sub-Gaussian random variable. That's basically what the theorem says. The other way around, from sub-Gaussian to normal, unfortunately not, because sub-Gaussian random variables can be discrete. Let's say Bernoulli, just 0, 1, or minus 1, 1. Just flip a coin. How can you construct a normal random variable, let's say normal, from Bernoulli? You can't transform discrete to a continuous, right? It's just one-way street.
But it's also ways around, from continuous to discrete here, yes?
Continuous to discrete, yes. Yes, you can do this by change of matter, yeah. Good. Any other questions?
But what this theorem tells us about from continuous to discrete.
Yes.
And I see. Okay. Yeah.
Yeah. It says from continuous to discrete. From any Lipschitz function of a normal random variable will automatically be sub-Gaussian. That's what it says, basically. Yeah, but not the other way around, unfortunately. Good. Any other questions? Thanks for that one. That was good, as usual. Okay. All right. Now, one application to this. This is beautiful, right? This is all cool. But how? What is a nice application of a Lipschitz function? Here's an application, very clear application, where the function is very natural, but also totally nonlinear. It's eigenvalues. So think about an eigenvalue of a matrix. Let's say fifth eigenvalue. How does eigenvalue depend on the entries? Can you just take the matrix and write the formula in terms of entries? No, right? Eigenvalues are very nonlinear functions. There is no closed form expression in them for eigenvalues. So that is a nonlinear function, and let's apply our theorem to it and see how it goes. The result is a very general theorem about concentration of eigenvalues of any random matrix. But in this particular case, let's have n by n, so a square symmetric random matrix. And here by square symmetric, I mean that we fix the entries above the diagonal, on and above the diagonal, are independent and identically distributed normal random variables, and the other entries are obtained by reflection. So that we make the symmetry with normal IID, independent and identically distributed entries on and above diagonal. Then, for any eigenvalue you would like to consider, let's say 17th eigenvalue, it concentrates near its expectation. Very nicely concentrates. It's sub-Gaussian, actually. Two e to the minus t squared. I get 4, but I think it can be improved for any t. So the point is, although the eigenvalues are very nonlinear functions, and actually we do not know the formula for them, closed form, we know that they concentrate very nicely. They're very close to their expectations, and the deviation is at most normal. But let's deduce it. It's a simple deduction. The eigenvalue is a function. We should think about the eigenvalue as a function of the matrix. It's some function of matrix. Now, technically, the theorem about Gaussian concentration applies to a function of a vector, not of a matrix. But we can vectorize the matrix. It would just concatenate the rows or the columns and imagine our matrix as a long vector. Let's do it. So to apply Gaussian concentration, we vectorize our matrix A. So we identify A with a very, very long vector. In fact, we don't have to include all the entries because by the symmetry, some entries are repeated. So we'll only include the unique entries on and above the diagonal. Let's call this vector A bar. So totally there's n square entries. And then the unique entries are, I think on and above diagonal will have something like this many entries. So these ones, the ones that are marked by the star, that's how many of them. And then we apply Gaussian concentration. For the function that takes the matrix, returns the eigenvalue, the ith eigenvalue. Is it Lipschitz? Let's check. This is what the ith eigenvalue of A minus ith eigenvalue of B. Gotta check that. What do we know about it?
Weyl inequality?
Yes, Weyl inequality. This is stability, exactly. Just a basic perturbation theory of matrices. Weyl inequality says that this is less than the operator norm of the matrix. We used Weyl inequality a lot in this course. Okay, so this is operator norm of the matrix. But we are like, oh, operator norm. We need to represent it as a norm of a long vector. It's a bad thing. So we need to pass from the operator norm to Frobenius norm. Remember, Frobenius norm is just a sum of the squares of all the entries, which corresponds to the Euclidean norm of this long vector. Euclidean norm is the sum of the squares of the entries. Frobenius norm is the sum of the squares of the entries, so they are in correspondence. So this is less than the Frobenius norm. Yeah, remember why? Yeah, the operator norm is the largest eigenvalue, largest absolute value of the eigenvalue. Frobenius norm is the sum of the squares of the eigenvalues. So that's why. Okay, less than this Frobenius norm, and the Frobenius norm is, I think, I need to vectorize. I think this is, let me think. So this here we look at all the entries, and here we look at just half of the entries, basically. This one, the ones that are marked by star. I think this is true. Because if you square both sides, the left-hand side will be the sum of the n square entries, all of them. The right-hand side will be twice times the sum of upper diagonal entries, and then it's true by symmetry. So we proved that F is Lipschitz. It's Lipschitz with this parameter, so it's √2 Lipschitz. That's it. Gaussian concentration, apply Gaussian concentration, we're done. Soft proof, right? We don't need to know much about eigenvalues, much about this function, just any questions about it? All right, let me ask you guys. Okay, so this theorem says that the eigenvalue, like any eigenvalue, is very close to its expected location with high probability. Good. So what is the expected location? How do we compute that? Let's say what's the expectation of lambda? Let's say n/3 of A. Totally, there's n eigenvalues, and I am breaking the eigenvalues in like 1/3 and 2/3 of n. How do you compute that? Where is it approximately? Do you know? Any tools that we studied? It's random metrics.
There was a distribution like this half circle law and the Mashenko-Pastur, or
exactly
the name of
yeah. Which one? So this is semicircle law. It's Marchenko-Pastur is for covariance matrices. That will be for the matrices like A transpose A. And the semicircle law is exactly for this situation. So that's semicircle law that we studied a time ago. It basically says that there is the limit in distribution as n goes to infinity. The histogram of the eigenvalues converges to the semicircle with endpoints at 2√n and -2√n. This is the kind of the limit in density of this eigenvalues. And if I want n/3, then I just need to break down the semicircle. So we have 1/3 area here and 2/3 area here. And that's the expected value. That will be approximately the expected value. Actually, exactly of that, where n goes to infinity. Yeah. Easy. This is not trigonometry. Just find the line that separates the area of the circle in 2/3, 1/3. So that one is easy. Any questions? Okay. Boom. That's his line, like red tape. We crossed it. You did it. Good. We did it. Concluding remarks. I'll first say some remarks for the record and then off the record. So now, first of all, we did a lot here. And if you need materials, and I'm sure you will need materials for this course later in your research or in your work, they're always available. They will always be available online. And also, you should know what are the further avenues, the further literature, maybe related, that covers a lot related topics and in more depth. So first is, you of course know my book, on which part of this course was based. Just let me give you one example. For example, what can you find there? You may ask yourselves, all right, so we did it for Gaussian measure. Cool. Is it true for non-Gaussian measure now? Is it true for discrete measure? Is there an isoperimetric inequality for Bernoulli, for example, distributions? And yes, there is, and there is in this book. So that's that. There is Joel Trop from Caltech. Joel Trop's lecture notes, also called probability in high dimensions. Again, there is some overlap. They're also based partly on my book, but also on his book. And this is probably the book that's closest to the level that we are at. So you can just dive in there, and there's a lot more in concentration. Basically, you'll see a lot more concentration inequalities there, useful ones. Joel Trop is the one who popularized and partly developed metrics Bernstein's concentration inequality, the one that we studied. For the more ambitious people, Ramon van Handel from Princeton also has lecture notes in the same topic, probability in high dimensions. This is more advanced. It requires some knowledge of functional analysis, but not too much. So that's kind of the next step up. If Trop is the same level, or maybe higher a little bit, but Ramon van Handel is the next step up in that. And it is not a long book. It's maybe like 60, 80 pages. Then for people who are specifically looking into data science, statistics, machine learning, Martin Wainwright from Berkeley has a book on high dimensional statistics. Also a lot of overlap with my book, which is good because it kind of builds from the same foundation, but it goes much farther into the high dimensional statistics area in sparse regression, structured inference. I can't remember if he has a deep learning there or not, but something like that. High dimensional statistics. It's a book that was published, in fact, simultaneously with my book by the same publisher, Cambridge University Press, in the same series, and we didn't know about each other. Good. So there are much more, but I'm not burden you with details. But these three sources are the most related and the ones that you can just dive in, and you're ready to read this. You're ready to use them as a reference, further reference. Any questions about the literature or further reading, further directions? Good. Okay, now guys, I want to say something. This was the most thorough, most intense, and most rich course for undergraduate students that I've ever taught in my life. So I'm really happy for you. I'm really happy for myself that we're able to pull it. You are now better prepared for research. If you're undergraduate or whether you're a graduate student, doesn't matter. You have a lot of tools under your belt that you saved yourself a lot of time, as I'd say. The other direction that I went through was to pick up all these bits from different pieces in the literature, and it takes a lot of time. My compliments to you, especially. Thank you for all of you guys who stayed with me during this extremely difficult semester in Ukraine, who studied hard, especially to those who did homework on a regular basis, especially to those who did most or even all of the homework. problems despite the hardships. This is amazing. I really, really admire your determination, and I hope that this was useful to you. Thank you also for all of you who joined live today and in other days. It's really helped me and helped other students shape this course. Your questions help to shape the conversations here. Especially thanks to those who asked questions during the class and who came here, who had to get out of their apartments to find place with internet and electricity. This is remarkable, and I and also other students are grateful for that. Also, thank you everybody who watched us offline and who was not able to join us. Let me now stop recording. Thank you, everyone. I will stop recording now, and I will continue to make remarks. Stay on. Stop recording.